Looks like we're live. Hello everyone and welcome to yet another recreational programming session with Mr. Azuzin. Let's make a little bit of an announcement and officially start the stream as usual. So red circle, live on Twitch. And what are we doing today on Twitch.television website? Today we're doing easy 3D in C with Raylib. How about that? So I'm gonna give the link to where we're doing all of that. Twitch.tv/studying. I'm gonna ping everyone who's interested in being pinged, and there we go. The stream has officially started. So what did we do on the previous stream? On the previous stream we were exploring the k-means clustering algorithm, right? And it's a very simple algorithm that, given like sort of like a points in some Euclidean space, which represent maybe representations or observations or something like that. So you try to fit them into k clusters, right? And it's actually very simple. Let me demonstrate you how it looks like. So essentially we generated 5 clusters in here. You can clearly see that there is 5 clusters, and so the colors of dot represents to which cluster it sort of belongs. And here we have centroids of the clusters. So the goal of the algorithm to find the optimum position of the centroids, so they correctly identify the clusters. So it's an iterative algorithm, and if you just iterate a few times, as you can see, centroids go to the center of the clusters, and there you go, we actually identified all of the 5 clusters successfully. Right, so it's actually kind of fun algorithm, right? So there's a lot of applications for this kind of stuff. And on the previous stream, I was a little bit struggling to come up with interesting application on the stream to implement, right? And then after the stream, I found such application, right? So, and such application is a color quantization. So the idea, I suppose, I haven't read like anything about color quantization, right? So I'm basically gonna try to guess how it works. So each point, each pixel is basically a point in a color space, right? And you take all of the colors, all of the unique colors, you put them in a color space, and you essentially feed them into k clusters, and there you go, you got a palette. You've got a palette, so you can basically now reduce the size of the image by using the palette that doesn't reduce the quality of the image too much, right? So for example, here we have 24 bits RGB color, and after the color quantization, it looks a little bit like less quality, but still the palette represents the image quite well. Right. So, and this is what k-means clusters can be used for, right? So, and as far as I know, it's originated in signal processing like that, right? So, and this is exactly what I want you to implement today. But since it's a color space, it is a 3D space, this kind of visualization that we have in here is not gonna cut it, right? Because it's a 2D visualization. It would be kind of nice to actually see all of the points in the color space in 3D, right, and see the actual clusters and stuff like that. That would have been cool. And luckily Raylib has such capabilities, right? So because it's a library that was developed for video games, right? So obviously it has 3D capabilities that we didn't really explore that much on our streams where we used Raylib, unfortunately. So I decided that that could be a very good opportunity to actually explore 3D capabilities of Raylib. What do you guys think? I think it's actually a pretty cool idea. So, and that's exactly what we're going to be doing today, right? So we're going to explore the 3D visualization capabilities of Raylib, right? And then we're going to use them to implement k-means clustering on 3D. And then once we have a k-means clustering on 3D, we can try to do color quantization, right? And try to maybe sort of like reduce the sizes of the image or something like that. This kind of stuff, by the way, is very useful for converting, for instance, PNGs to GIFs, right? So because GIF has sort of like a mode where you can basically store a palette, right? Instead of like a full RGB colors, you can just like provide the palette, and the palette can be provided, I think, in RGB colors, right? So you can basically compress some images, right? So essentially, if you say each pixel is going to be one of the 16 colors, right? So you can actually store such thing in a few bits somewhere, like you greatly compressing the image itself. You can come up with a format like that. So yeah. All right. So let's go ahead and see what we can do. Like, to be fair, I think I never tried 3D capabilities of Raylib. I think I tried them one time, long time ago, but I think Raylib was, well, I mean, Raylib didn't really change that much, but I feel like it was different. I was different, and I forgot everything, so it was a long time ago. So anyway, let's try, let's try to learn all of that from scratch. So I'm going to create a separate executable, right? So because we already have a lot of stuff in the previous executable here related to 2D stuff, right? So it's kind of difficult to integrate 3D stuff in here. So I want to start from scratch. So I'm going to keep both of these things like side by side. Right, I'm going to keep them side by side. So the first thing we're going to do, we're going to create a simple hello world. How about that? So I'm going to do it like this. So the usual thing, stdio. So print f, and we're going to do hello world. Hello world. And I'm going to go into my build script, right? And I'm going to try to just build it. So essentially, here is the command line that builds a single executable. And what I'm thinking is that maybe I'm going to factor it out because I'm going to use the same command line for building the second executable as well, right? So let's actually do something like build program, right? Build program, and we're going to accept the source path in here and maybe the output path, right? So the output path, all of that is needed for these things. So this is the output path and this is the source path, right? And then we're going to basically factor out this entire stuff to here, right? Like so. So, and I'm going to replace this thing with the output path and this thing with the source path. So, and then we are running it in here. So, and if it returns false, that means it failed. But I think I'm going to propagate the result of this thing, to the caller of the function, right? So that then they can see if that particular command has failed or not. So interestingly, I think I want to do something like this, right? So the command object has to be in here. So, and we have src main.c and the output is k-means, right? So, and this entire thing fails, we're going to return non-zero exit code, right? There we go. And if now I want to add another program that I want to build, I just have to clone this command, clone this line, and just do 3D. So now we're building two of these things, right? So now I can just go ahead and run knob, and it built both of the commands. So now I have k-means, and now I also have the second command 3D, which is hello world, right? So I have a very simple build system, and as you can see, it starts to slowly evolve, right? So now I can support multiple executables in here, which is pretty cool, right? So if I want to make it work on with MSVC, for instance, right? So the only thing I'll have to implement this particular function differently, and all of the logic in here is going to stay the same, right? So maybe this kind of stuff at some point I'm going to factor it out like right into the knob, right? So maybe there will be sort of like a very simplistic cross-platform builders, right? That allow you to just say, okay, build the source path with the output, and depending on the platform, depending on the current platform, whether it is GCC, MinGW, MSVC, Clang, or something like that, just do that differently, right? So something very, very simple, and maybe some capabilities to add include path, so to abstract away some of these things. It's gonna work really well for simple things, right? So, but for more complicated things, which you want to fine tune, you will still have to use an opcmd, but that's fine. That's what you end up doing in CMake anyway as well, right? So if you need something that goes outside of the framework of CMake, you still go down to like commands, right? So, and they're not particularly cross-platform anyway. So I think that's fine. I think that's fine actually. All right. So what we're gonna do, we're gonna create the usual boilerplate with Raylib, right? So this is gonna be raylib.h, and we're gonna init window. This is going to be 800, 600, 3D, k means, there we go. And while window should close, while it should not close, while it should not close. We're gonna begin drawing. And as far as I know, in 3D, this is not how you do Scheisse in 3D in Raylib, actually. Right, so let's actually see. I think you do begin mode 3D, right? So begin 3D mode with custom camera, But to be fair, maybe you still have to enclose that stuff within begin drawing and end drawing, right? Because yeah, okay, I see. So essentially, you even have like mode 2D. So you need mode 3D specifically for the camera. And what is the camera? What kind of parameters does it have? Right, so you have a position, target, so the point which it looks at, camera app vector rotating over its axis. Oh, okay, so it allows you to, yeah, I see. So you have a target, you're looking forward, and then you have the up, and that up allows you to maybe like rotate thing or whatever. So field of view, right? So camera field of view, aperture in y degrees in perspective, and projection. So camera projection perspective or orthographic. So obviously we're probably going to be doing perspective, but maybe orthographic is also going to work well. Right, orthographic. Basically, do you guys know what's the difference between perspective and orthographic and stuff like that? So I can actually show you, essentially. Just a second. So it is actually super easy. So essentially in perspective you have vanishing points, right? So if you looked into the far, you've noticed that the objects in like the farther they go away, the closer they are go to the center and the smaller they become. And they sort of converge into a single point. That is called a vanishing point. So and essentially if you want to draw a cube in perspective, like in this like sort of perspective, what you have to do, you essentially draw sort of like a square. Right? So you draw a square like so, super easy. And you take all of these like corners and you move them towards the vanishing point. You move them towards the vanishing point, like so. Right, and there you go. Here you have the edges of that cube. So essentially you can sort of draw a smaller version of that cube in here, like so, and there you go. You essentially got a cube that is in perspective. You can actually remove these helping guides and stuff like that. So, and you can draw that thing in different places, actually, right? You can draw them in different places, and depending on their position on the screen and how close they are to the vanishing point, the cube's gonna be different depending on the sort of like a perspective. Right, so the main sort of difference in here is that they have a vanishing point. So, and you can actually draw a lot of them and they're gonna look like they're sort of going out of this vanishing point. So it's actually kind of cool. So orthographic is just like the usual thing. You have this face of the cube and you have the second face of the cube, which is pretty much the same size. Right, and it's just connected like that. So there's no any vanishing point, there is nothing in there, nothing is vanishing, everything is just like the same size. So this is orthographic. And usually in games you have perspective, right? So this is basically what it is. So so that's the difference, like without going into the math of all of that stuff, right? Just basically like in an artist's terms, right? Because the technique that I showed you that to draw perspective things with a vanishing point is actually the technique that artists use, right? So artists actually use you know, these kind of vanishing points and stuff like that to draw perspectives and everything. So anyway. So I guess that's the main difference, I think. So yeah, I just wanted to make sure that we understand all these fields. Hopefully I did understand them correctly. Anyway, so let's do begin drawing and then end drawing. And in here we're gonna you know, clear background with, let's go with a green color now, right? So, and after we're done with all of that, we're gonna close the window. Close the window, close the window. I'm gonna rebuild this entire stuff, and there we go. So we've got a window. We got a window with the green color. All right. So I wonder if there is any way to create camera 3D. Camera 3D. So there is an alias to just camera for camera 3D. So I suppose everything that returns just a camera refers to camera 3D specifically. Right, there's different camera modes. I'm not really sure what the fuck all of that is supposed to mean. Maybe I want to try to use Google, right? Because I want to find maybe a function that returns sort of like a default camera. Right, so I want to have a default camera because obviously I'm not, you know, filling up all of these things myself, right? So I don't really know what I have to put in here. Do I fill it up myself? Right, it would be kind of nice if I just had some sort of a default camera. Right, I wonder if I can just use Google. Right, so Google. I forgot how to use it, by the way. Does it tell me how to use itself? Okay, so it does in fact tell me how to use it, right? That's actually pretty cool. So I'm going to do Raylib, and what I'm going to be looking for, I'm going to be looking for something that returns camera, right? Does anything return a camera in here, right? So nothing really returns a camera in here, surprisingly. Is anything like accepts the camera? Right, so maybe I have to do it like that, so camera void. Nah, nothing. So I suppose things only primarily accept the camera, right? So that means I have to build it myself. There is a get camera matrix. Right, that's very interesting. Oh, okay, so it's just like a transformation matrix for that specific camera. All right, that makes sense, I suppose. Okay, that means that we have to create the camera ourselves. Sure, I mean, we can do that. Camera, 3D camera. I'm gonna initialize this entire thing with 0 for now. Right, so let's clean everything with, you know, the background color, right? So let me see, get color. I'm going to be using the usual color that I like, 888888, so that's my favorite color. And in here, we're going to do begin mode 3D. We're going to provide the camera. And then we're going to end mode 3D. So maybe since this thing act like sort of brackets, I think it makes sense for me to maybe indent this entire stuff, right? So, and we have to draw something here. And I wonder if I can simply draw a cube. Is there any way to draw a cube? Draw cube. Okay. We're already good to go. Look at that. What the fuck? So if you want to draw a cube, you can just do it in here. So position, what's going to be the position? Let's say that position is going to be maybe 0, 0, 0, right? So something like this. So this is going to be the position. And I'm going to just initialize all of that. I might as well do something like, oh yeah, I can do vector 3, 0. I'm pretty sure something like that does exist in Ray Math, right? So vector 3, 0. There you go. I do remember that. There we go. That's pretty cool. So it's going to be width and height. Right, I suppose we can say that it's going to be maybe 1, right? So it's a 1 by 1. Right, so width, height, and length, 1 by 1 by 1. And this entire thing is going to be red, right? So there you go. So we have a cube. It would be maybe kind of nice to actually do, let's say, position is going to be -1, -1, -1, and width, height, and length is going to be 2. So it's like center mass is at the center of the coordinate system or something like that. Right, because of that, I think I'll still need to create position in here. So this is going to be something like vector 3 position, right? So this is the position -1, -1, -1, something like that. And obviously, we're probably not going to see anything because the camera is completely uninitialized, right? So nothing really is happening in here. So let's go ahead and just like rebuild this entire stuff and see how it goes. Right, so it doesn't build because I don't have to provide anything in here. And there you go. We've got some things. We see nothing. We literally see nothing. Isn't that a poggers? I think that's pretty freaking poggers. Okay, so let's try to we can take a look at some of the examples. We can try to take a look at some of the examples, but I want to try to figure out that shit myself, if you know what I mean. I want to figure out that shit myself. So Raylib actually comes with a lot of different examples and stuff like that. I can take a look at them. I have a source code in here, and here are examples. Oh, I actually stripped examples off of the Raylib in Visualizer. Do I have a source code in anywhere in here? So I do have a source code in here, so I might as well take a look at the examples in here. There you go. And there should be something like shaders, models. Would you look at that? Right, so draw cube, texture, right, so how many just cubes, waving cubes and stuff like that. So there's this example that draws cubes and stuff and everything. And I could look at that, at those examples, but I don't want to. I just want to see how intuitive the API of Raylib is by itself without any examples. Examples are actually the best way to document library, in my opinion, right? Because we kind of learn like artificial intelligence. We are intelligence, right? So it's just like we learn by looking at examples and sort of extrapolate to the rest of the things, right? So we just need some points in the you know, on a graphic, and then we can extrapolate and understand how the entire thing works. So but something that is even better than examples is actually an API itself, that you can sort of derive how to use that API by looking at the signatures, by looking at the types and stuff like that, right? So something like that is even better. And Raylib is actually super good at that. Surprisingly, it is super good at that, right? It keeps everything super simple, so you can kind of like, look how quickly I found how to draw a cube. We still can't draw any cube, we still can't see any cube, but I can imagine that I just need to position the cameras like correctly, right? So that's what I need to do. That's what I need to do. So the position of the camera, I suppose, since I said it's 0, it's 0, 0, 0. So that means we are inside of the cube, if that makes any sense, right? So we are inside of the cube. So what we have to do, we have to go somewhere outside of it. So I suppose the usual thing is that you have like X and Y, so X and Y coordinates in here, and Z either goes like forward or it goes backwards. I don't remember which one is like Raylib uses in here, right? Which one Raylib uses in here, but maybe we can experiment with, maybe we can just see how it goes. So anyway, so let's go ahead and just try to craft the camera. So we're gonna do a position. So the cube is 2 by 2 by 2. So, and essentially, if we position ourselves at 0, 0, 0, we have to go sort of like a backward by 2. Right, and we're going to assume that the Z goes forward, so we go backward by 2. So that means we're going to have 0, 0, minus 2, right? Maybe we can even create some sort of a cube size, right, which is going to be 2, right? So it is going to be 2. And because of that, we're going to just subtract the cube size. So this is a cube size. Here, we are having something interesting. So this is going to be minus half of the cube size, right? So this is minus half of the cube size half. So that way I can kind of control this kind of thing, and all of that stuff is the cube size. There we go. So here we can maybe specify cube color, something like this. So cube color is going to be red. And what that allows us to do, is basically position ourselves at Z at cube size minus cube size half, but also plus 1, so you have a little bit of a space between your eye and the cube, so you can see the cube. Or maybe we can actually always go twice of the half of the cube. Twice of the half of the cube. It's a full cube, yes. Twice of the... That's really funny, but anyway. Twice of the half. This is such a funny phrase. Twice of the half. I really like it. It's 1, yes. Sorry, it's 1. Anyways, so what's going to be the target? The target is obviously going to be the cube itself, which is positioned at effectively 0, 0, 0, right? So this is where it's located. So up, so rotating over its axis, the camera vector And I don't really know like how to do that. So let's do up, and it's going to look up, right? So that means z, x and z are going to be 0, and what's going to be y? Y is going to be up. So that's what you want from me, I suppose. That's what you want from me. Okay, so I can provide that. No big deal. FOV. So I'm really glad that you specify that it's in degrees, right? So because I had a couple of weird situations when I couldn't understand why my shit doesn't work, and this is because I was using radians instead of degrees. But to be fair, Raylib is kind of consistent on using degrees when it comes to angles. That's kind of interesting, actually. I wonder why, though. So I suppose Raylib was initially designed for teaching people programming and teaching people computer graphics, like in schools, in universities, and stuff like that. And obviously, the students have math courses, and all of the math courses they use degrees, right? So I suppose to help people accommodate for that, so they just decided to let's use degrees all the time, right? Because it makes sense. You can just use some of the formulas that you learn in a math class, right, in here in the programming class or something like that. So the major sort of difficulty that you face when you come from math to programming is just getting used to using only radians instead of degrees. But maybe, I don't know, maybe professional mathematicians also use only degrees, I don't know. So in terms of projection, we can try to use orthographic just to see how it looks like, and I have to specify FOV, right? So let's actually specify maybe 90 degrees, right? So it's going to be 90 degrees. So projection is going to be right. Let's try orthographic and see how it goes, right? So this is going to be just orthographic projection, and there you go. We kind of specified everything, hopefully we specified everything, so let's see how it goes. Target, did you mean oh. Okay, that's very interesting. So how did I put that dot in here accidentally? So I have a compose key. All right, so I have a compose key that allows me to do these kind of things. Right, so which is kind of cool. So I suppose, yeah, I can see that. So if I hold compose and then T dot, it actually puts a dot in here, right? So I can actually type a lot of special Unicode characters and stuff like that. Yeah. So in Russian language, we use these kind of quotes instead of usual these kind of things. Right, so this is more like they're not really Russian. As far as I know, they're French quotes, right? So we stole that shit from French, if I remember correctly. Greek question mark moment. Yeah, exactly. Greek question mark. Okay, so, and we can't see Scheiße in this mist. We literally can't see Scheiße. Okay. So we can try to understand why. This is maybe because we're coming from a wrong position. So essentially, I assume that Z goes forward, right? Z goes forward. Maybe it actually goes backwards. In that case, right? So what I have to do, I have to actually do something like this. Right. So let's see if it's going to change anything. There we go. So yeah, that's how we figured it out. So forward is actually negative Z, right? So how do you, so I know that there is a left-handed coordinates and right-handed coordinates, but I can never remember how do you determine? Okay, so essentially you have X and Y, right? So you X and Y, you align your thumb to X and you align your pointer to Y, right? And depending on on your hand, the Z is gonna point in different directions. So I suppose this is a right-handed coordinate system, right? Because I just align my thumb along the X and I align my pointer along the Y, and the middle finger points I suppose, towards me, so the negatives go that. So because of that, this is a right-handed coordinate system. Did I understand that correctly? Because I'm not a graphics programmer or anything like that. Right. So this is a right-handed and this is the left-handed. So this is correct. Okay, so do we even have a mention of that in here? Right-handed. Yeah, okay. Holy shit. Yes, they taught me this in school. Yeah. So the only thing I remember in school is that you have to just align some of your fingers with some axis and some other finger will show you something, but I don't remember the details. So I just went with the most logical thing. All right, so the most logical thing is just like, yeah, and I actually guessed it. That's actually pretty cool. Huh. So it's like big engine and little engine and stuff like that. Anyways, so we can, so this is the orthographic projection, right? So this is specifically orthographic projection, and we are not particularly interested in that, I think. We're more interested in perspective, right? But I have a feeling that with what we're drawing on the screen, this is not going to be that much different, right? So this is not going to be that much different, right? So there's like nothing that indicate, yeah, there we go. So that is kind of bizarre, honestly, right? So, why is it only a half? I have no idea, honestly. So we need to understand why. So in the perspective, it's actually this. Right, I would expect it to, okay, so this is the target. This is another thing. So the position is half of the negative. So, and then you get the full thingy and that should work, but yeah, it's kind of weird. It's kind of weird. But anyway, so if I try to increase the size of the cube, nothing really changes, right? So because we scale all of the positions and like literally everything along with the size of the cube. So literally the size of the cube doesn't really matter. And maybe because of that, we can just like put something a little bit bigger than what we had in here. So we can try to maybe move around a little bit, right? So we can introduce something like is key pressed, and essentially maybe is key down, right? Maybe if is key down, key, let's say S, right? So we're going backwards. And as we go backwards, we can take the camera position, specifically Z, right? So, and we can keep incrementing it by some sort of a speed, right? So let's actually say camera speed multiplied by delta time. And of course, delta time is the get frame time, something like this. So that allows us to go backwards, right? So because forward is a negative Z, and we can try to go forward as well. So this is a very simple condition. I can actually make it something like this. So if key is down W, right, so we can do subtraction in here, right, so we can do subtraction. Okay, so let me see if we can do anything about that. So the camera speed, let's define le camera speed, and let's say that maybe it's going to be the cube size, right? So we're moving cube size per second, right? Cube size per second. So is it going to change anything? Yeah, there we go. We can move you know, forward and backward and stuff like that. That's pretty cool. I still do not fully understand why the cube is located like that. I specifically crafted the cube so it's at the center, but maybe I am actually wrong. So maybe what you're doing, so let me take a look at the implementation of the draw cube. Okay, what I thought is that you specify the position of the corner, and then you specify the sizes, so the width, height, and length and stuff like that, don't freaking tell me that what I'm doing is specifying the position of the center and then the rest. So I do specify the position of the center. So because of that, I would expect in Raylib, when I draw the cube, I would expect it to be called center or something. I would expect it to call center. We can actually confirm that. We can actually confirm that by looking at the source code, right? So always just look at the source code. Source code is the best documentation. You know why? You know why source code is the best documentation? Because it is never outdated. It is never outdated, because if it gets outdated, your code doesn't fucking compile. You're literally forced to update your documentation before you can compile it. The actual human readable documentation, nothing actually checks whether it's up to date or anything like that, right? So it can go stale very easily, right? It is very trendy and it's very fashionable today to say, oh, look, in the future, the AI is going to do that. Okay, sure, yeah. Judging by how AI treats the factual information, right? So, okay, so let's take a look at the implementation of that specific thing. I wonder if there's like R models. Okay, so draw cube. Okay, so you have this guy, and of course, they even take half of the width. Ray-sama, why didn't you call it center? Cube position, yeah, of course. Why don't you have this node in a header where it's needed the most? Like, come on, seriously. Like, less people are gonna look into the C files rather than the like H files. Like, come on. But maybe it's said somewhere in the examples or documentation or something like that. I mean, yeah. Anyway. So, all right. So you're supposed to actually provide the center. Okay. So all of that scheiße must be 0. And that means all of that has to be 0. And yeah, there we go. Might as well just do vector 3. So my initial thing was correct, apparently, right? So this was correct. Okay, go. So vector 3, 0. So I need to do array maths. Ray maths. Okay, go. So you can't really see anything much, right? So especially perspective, because it's such a solid thing. We need to implement some sort of a rotation, right? We need to implement some sort of a rotation. By the way, I think I want to try to make the window resizable, right? How do you make the window resizable? I do remember there was some sort of a special flag, there you go, to make the window resizable, right? So now I want to see what's going to happen. Oh, it actually adjusts everything. All right, look at that. So, yes, so this is almost like a 3D game. Does it feel like a 3D game, chat? I'm like, okay, I'm moving backwards and I'm moving forwards. This is a 3D game, clearly. This is a 3D, clearly. Anyways, so we can try to actually move like left and right, why not? So if is key down, key A, so this is moving to the left. So camera position X is going to be essentially, well, so if we're gonna start messing with the rotations and targets and stuff like that, this is gonna be a little bit painful, right? So, because this is not how it all works, but we'll see. So X, so this is gonna be minus X minus camera speed dt, and then we're gonna do d, it's gonna be X plus something like this, right? So I can, oh, this is okay. Oh, I know what is going on because the target is the same. Holy shit. Okay, I see what's going on. I see what is going on because the target is the same. Right. So because we still, okay, that makes sense. But at least we can see that it is 3D. Okay, at least we can clearly see that this is 3D. Right. I'm moving left and right, but since target is locked at 0, it's just like, yeah. So that's kind of funny. So I think it may make this kind of shit a little bit easier because we can render our scene, our stuff around 0, 0, 0. We can lock the camera looking at 0, 0, and we can just have a vector that moves around, and it's always going to be looking at that center, at that scene, which is extremely convenient, right? So when you have a bunch of points and stuff like that, so we can basically bind like a scroll, mouse scroll, on making that vector longer or shorter, effectively zooming in and zooming out. And for moving around, right, so we can just like update the angles of that vector or something like that. Right, so you can hold mouse down and you'd like move it around and you can just like update certain sort of angles. So that makes a lot of sense, I think. That makes a lot of sense. Maybe we can represent like a, you know, that specific vector as two angles, right? So there is like an angle for the X and Y and another angle for the other thing. And that way you can control all of them. Yeah, that's a lot of fun. That's cool, actually. I really like that. So I wonder if I can like literally implement that. So essentially, we have a magnitude, camera magnitude, which is initially going to be, let's say cube size, maybe even twice of the cube size, right? So this is initial magnitude. And so you essentially are going to have two vectors. So I didn't really know the conventions on how people call these vectors, but I'm going to call them alpha and you know, beta, right? So sort of two vectors. You know what vectors I'm talking about, right? So right, if you have 3D and shit like that, does anybody remember how they're called? Right, because I'm not a math person. I do not fucking know shit. I do not know shit. I just fuck around until I find out. Right, so Z. So the first angle is this one. So, and then the second angle is like this one. So that way you can kind of represent theta and alpha, right? Theta and alpha. So, but the first one, this one is alpha and the second one is theta, right? So something like this. Which one is which? Alpha, beta? Yeah. All right, so I'm gonna call this theta. Theta, sigma, ligma, ligma. Okay. Anyways, so instead of updating the camera like this, we're gonna actually, you know, do that slightly differently. So, and that means the camera should be computed at each individual frame effectively, right? So because the actual state of the camera is this, not this. We are converting like the magnitude and two angles to this specific camera, right? So that's basically what we're doing. So, and in here, we're gonna have le position. So let me try to see how we're gonna do all of that. So we have X in here. So an X, if I'm not mistaken, it's a cosine of alpha multiplied by the magnitude, right? So this is a cosine of alpha multiplied by the magnitude, and Y is a sine of alpha multiplied by the magnitude. So what's gonna be the Z? What's gonna be the Z? Does anybody remember? So maybe, by the way, maybe we could just use matrices. I know that there is a matricing, so something like rotation. So quaternions. Transform vertex information data. Maybe we can use that scheiße. Maybe we can use that scheiße. Rotation, scale, quaternion. I remember using quaternion like once. And X, Y, Z, W components. I don't remember what these components mean honestly. So, and where do I put transform? I put it into the model, right? So can I, so I can get the matrix of the camera specifically, but can I construct like a camera out of the matrix? Right, I know that nothing really returns the camera, so the answer is probably no. The answer is probably no. So get collision between ray and mesh, and also, oh yeah, so that's probably the reason why you can get the matrix of the camera, right? That's why you can get the matrix of the camera, because then you wanna check some collisions within the camera space or something like that. So a quaternion defines a line from the objects x, y, z and the rotation w, usually in radians. Okay, so that makes sense. You know what? I think I want to make a small break. I want to make a small break and make a cup of tea, because I'm already streaming for 1 hour. Right, so, and after the break we're going to continue figuring out how to sort of like represent the camera. So I want something simple, right? I don't really want to overcomplicate anything, right? So we just need to be able to maybe just like fly around the scene, and that should be pretty straightforward, right? That should be pretty straightforward. If we're going to struggle too much, we can always look at the examples, but I'm going to use examples as the last resort. The most important thing for me is to just figure out things myself, because that's how I achieve understanding. I know it is laughable in 2023, already almost 2024. So the current sort of like trend is that the less you understand, the more successful you are. And you think I'm exaggerating or joking or anything like that, but look at the current web. The higher you are in abstractions and the less you understand, the cooler you are, because you're so effective and get so much done. Doesn't matter that the website is dog shit slow and you know, crashes all the time. That doesn't matter. Like, look how fast I am. And if you try to understand how their stack works, you are called wrong, right? And especially, right, so with the rise of AI, right, so understanding of things is actually even lower, like, you know, the reputation of being able to understand things is even lower, because why? You can just ask ChatGPT. So look, the less you understand, the more successful you are, right? So, and so I understand that trying to understand the library is absolutely laughable in 2023, because that's a sign of a loser. That's a sign of unsuccessful person that never gets anything done. But maybe I am. Maybe I am. I'm also a person that ran out of tea, so let's make a small break. All right, so on the break I just remembered that, so the thing I'm thinking about is probably the polar coordinates, polar coordinate system, right, this one. So in a polar coordinate system is literally two angles, at least in 3D. And a length, right? So in 2D, it's one angle and the radius, right? So, and in 3D, I wonder, like, this Wikipedia page is kind of weird. So does it do 3D? Extension in 3D, so cylindrical coordinates, spherical coordinate system, right? So that's, yeah, this is what I was thinking about. It's a spherical coordinate system, because polar coordinates in 3D, they have two sort of flavors, right? Cylindrical ones and spherical ones. So I suppose in here we want spherical ones. And we want to be able to convert them to Cartesian, Cartesian coordinate system. Right, so is there any sort of conversion? Okay, so this is a conversion from Cartesian to this thing, but from spherical ones to Cartesian is actually super easy. Okay, so there's a theta and gamma, right? So this is a phi. I don't know Greek alphabet, I'm sorry. Okay, listen, in my life I already had to learn two alphabets, right? Latin and Cyrillic one. Don't just cut me some slack. Why do I have to learn a third one now? Come on. How many goddamn alphabets do I have to learn? Like, Why people keep making alphabets? This is phi, right? So this is, come on. Phi, yeah. So I guessed it correctly and accidentally pressed Control Q. Thank you so much. All right, spherical coordinate system. I can actually open it up. And by the way, I suppose it makes sense to actually add it to the, to the description, right? So Wikipedia, spherical coordinate system. So, and in here, we can be sure that this is more of a theta and this is phi, right? And this one is, we can even prefix it like that, camera, theta, phi, and magnitude, right? So this is basically the different state of the camera, right? And I kind of really like that. So let me see. So conversion, coordinate system conversion. So X has to be this kind of stuff. So we get the magnitude, and then we take the sin, and this one is theta, and then multiply by cosine of phi. Right. And then here we have two sins, theta, phi. Speaking of understanding, right? So doesn't be like, I want to understand everything and then mindlessly retypes the formula from Wikipedia. So yeah, being hypocritical like that, am I right? So, but I will understand it eventually. I'm pretty sure I can derive that formula. It's just like, it's one of the things that you have to sort of like derive once and then reuse as a black box, maybe. Probably. Who knows? It's like, for example, formula for barycentric coordinates. I kind of know how to derive that formula, but I don't remember it off the top of my head. Right. So it's just like, how am I supposed to remember that? Like, I can't remember that, honestly. Right. So I can derive it, right? Then write it down somewhere on a sheet of paper, or maybe save it on a computer. But remembering that is just like, we got a raid from Pro. Thank you so much for raid. Yo, what's up? What's up? What's up? What's up? What's up? What's up? So yeah, essentially we're trying to do 3D using Raylib. Not only 3D, actually. The main goal here today is to do k-means clustering in 3D space. We're just using Raylib for visualizing that 3D space. Right? So that's what we're doing essentially. And up is kind of annoying, right? Isn't up supposed to? God damn it! Maybe it's fine. Maybe it's fine. Right. So I'm gonna just keep it as it is right now. All right. So that seems to be fine. So one of the first thing I would like to do, I would like to maybe handle the wheel, right? So get mouse wheel movement. So this is get mouse wheel for X or Y. So, and essentially, if we try to maybe handle this entire thing, so get mouse wheel, float wheel, if wheel not equal 0, we're going to just print it. I want to see what's its value, right? Is it from 0 to 1 or like -1 to 1, or is it something else? Because I think it's quite important. Okay, so it's -1 and 1, so that's important, right? So that is in fact important. So that means what I can do is essentially take the camera magnitude and add. Well, to be fair, right? So you probably want to multiply, maybe not multiply. Let's actually do add plus wheel multiply by cube size, right? So say that a single sort of like a click of the wheel, right? So is going to be like 1 cube size. Let's see if it's going to work. And it doesn't freaking work. Something is wrong, and unused thingy in here. So literally nothing happened. Literally nothing happened. I'm actually quite surprised. So maybe because it has to be bigger or something. So do we even use camera magnitude in here? Like, wait, why nothing happened? Why nothing is happening? Oh, okay. I see. Maybe one of the things, okay, we can introduce something like camera magnitude velocity, right? So let's call it vel, and initially it is 0. So I think it's going to be way cooler, right? It's going to be way cooler. You have camera magnitude plus camera magnitude velocity multiplied by dt, right? And when you do a wheel, you basically do camera magnitude velocity plus the value of wheel, right? We can even maybe inline this entire thing, multiplied by the cube size or whatnot. Right. So, and what's interesting is that with the camera magnitude velocity, you can basically keep making it slower, right? So you can add a little bit of a friction to the camera. So that way you can have a little bit of a smoothing, right? So which is kind of cool. So, and to be fair, when I scroll up, I would like to actually, you know, go forward. That's what I would like to have. Yeah. So that seems to be kind of working. But maybe it has to be even faster than that. So what about like 5 times of the cube size? Yeah. That's pretty cool. So, but maybe when we do this kind of shit, we have to take the absolute value of the camera magnitude. Yeah. Maybe even further, what if I do something like this? All right, absolute value always. FABS, of course. But maybe it's not a particularly great idea in the sense that simply don't allow magnitude become negative, right? So if camera magnitude is less or equal than 0, actually less than 0, just make it always equal to that. Just make it always equal to that. So I think that's a, yeah, that's a good one. You're still gonna go inside of this thing, but that is fine. So we can actually make it not 0, but more of a like a cube size half, right? That way it's gonna always stay. But to be fair, it doesn't really matter, honestly. It doesn't really matter. Because this is not what we're gonna have on the scene, right? So it doesn't matter. So now we wanna start rotating, like changing different angles, right? So if, for instance, how we're gonna be doing all of that in a Raylib, there was get mouse delta. This one is a very interesting, right? This is a very interesting thing because it gives you a vector 2. Right, and effectively it is a delta of x and y, and you can use this thing to update theta and phi effectively, right? So essentially we can try to print this kind of stuff. So if delta x plus delta y is not equal to 0, we can try to just print them and see. So all of that should happen only if is mouse button down, mouse button left, right? So while we're holding the thing, right? While we're holding, because that's what we're going to be doing anyway. All right, and then here we can say f, and this is a new line, delta x, delta y. There we go. There we go. Yeah. So we probably want to have absolute values, right, of these things. Fubs. So that's what we want. Fubs. We want to have absolutely absolute values, right? And also normalized, right? No, not absolute, normalized, Jesus. Maybe because of that we want to normalize this thing. Does Raylib come with normalizer? So math normalize, and how does it normalize in case of a, okay, so in case of a 0, if this entire stuff is 0, it just like doesn't normalize, which makes sense. Okay, so one of the things we can do vector to normalize, and there we go, we have a delta that is normalized, and which is basically right, but it's not -1 or 1 or anything like that. Doesn't freaking matter. Anyway, so what I need to do, I'm gonna just assign x and y on theta or phi. Camera theta plus delta x, and let's see how it's gonna go, at least for the x. Right, so it goes too fast, so let's actually you know, reduce the you know, the impact of this thing. Okay, so that's already cool. And we actually want to do minus, right? So we actually want to do minus, something like this. Yes, yes, yes. So that's pretty cool. And we want to do phi as well. So, but only for y. And I think this is where it will go haywire. Yeah. Because I feel like, yeah. So there's something about up. There's something about up. We also need to keep updating up, unfortunately. We need to keep updating up. So essentially, this is my hypothesis, but I'm not 100% sure as usual, because I'm a dummy dum-dum. All right, so you have 3D scene. You have 3D scene, X, Y, Z, and you have your, like, you're looking at the center in here, right? So you're looking at the center in here, like so. This is where you're located. Your position is defined with the magnitude theta and phi, right? And you have also this up vector, right? You also have this up vector, and I suppose it has to be perpendicular to like you in here. It should like point in some certain direction, and I wonder how the fuck would you do that? So I'm not 100% sure how the fuck we will do that, but maybe I don't want to do it right now. So what I'm gonna do, I'm gonna just only allow rotation horizontally, and that is gonna be it. Like allow vertical rotation, because I already spent way too much time on rotation. I don't think it is particularly healthy. So we're gonna call it done for the rotation, and let's actually move on to implement k-means clustering in 3D, because that's exactly what we want. So we can take a look at our 2D example. In 2D example, we had samples, right? So, and the samples were in 2D, right? The samples were in 2D. We can port this thing here, and we can call it 3. Maybe it would make sense to actually call it like 3D samples, and this one is going to be 2D samples, right? So obviously it will create compilation errors through which we'll have to go, right? So samples 2D in here, right? So boom, that's pretty cool. So now we have some sort of 3D samples. And in a 2D example, we had a function like generate cluster, right? Generate cluster would generate you a cluster in a particular center, right? It just generates your cluster in a particular center. And in here, let's actually do vector 2, vector 3, boom. And we're using samples 3D, samples 3D. So we are generating this thing in a particular radius. Here is an interesting thing. This is radius in 2D, and the formula for this kind of conversion is going to be useful for us as well. I wonder if Raylib has something for polar coordinates. Polar, yeah, okay, Ray math. polar. It doesn't have anything about polar coordinates. What a shame. Seriously. Because polar coordinates are like quite often used in game development, I think. I think they are. I remember when I was a kid in school and I was learning about game development in C++ and stuff like that. Like I had a book about that, and it said that you know, polar coordinates quite often used for like turrets, right? Because you need to sort of point a gun in a certain direction, so polar coordinates are quite often used there. Something like from angle could be. Yeah, so let me actually see. So ray math from angle, from axis angle. Oh, get rotation quaternion for angle and axis. Wow, maybe I can use that. This is actually convenient. Again, I'm using way too much time on rotation and stuff like that. I should stop, actually. I should literally stop, right? So because otherwise I'm not gonna get anything done for today. So essentially what I want to do for the cluster, right? So I need to generate not only random magnitude, but also random theta, and a random phi, right? And this is what I'm going to be converting in here to the sample. So there we go. We can rat hole about rotation after I'm done with k-means clustering, because I feel like it may take too much time, unfortunately. I wish I could do that, right? But we have a limited time, limited air time. Okay, so we have like a generated clusters and everything, so that's pretty cool. Let me try to compile this entire thing. So let's go to the compilation errors. Rand float, this is a function that I introduced in 2D. Right, I would like to actually maybe rename this file to 2D, if you know what I mean. Right, so that will require also updating the build script. Right, so this is basically 2D, and this is 2D. You have 2D and 3D, two separate things, and I think that's pretty cool. Right, so rand float. And we could probably have something like a common C in here, and we can move some of the things there, like for instance rand float. I think it is very useful for both of the examples. I do think so. Right, even though it's actually like a single function, but does it really matter? Does it really matter? So let's include common.h, and for 3D let's also include common.c. Was it? It was C actually. There we go. So that way we can do that. So rand is not really available. This is because we need to include stdlib. Not a big deal. Not a big deal at all. And also in 3D, we need to include knob. We are reusing knob because it has a lot of useful stuff in there. Knob implementation. There we go. So we got some stuff, some warnings and everything. So center is not particularly used in here for some reason. And this is because I never actually add it, right? So if I do generate cluster, one of the things I do in here, look, I add the center. So that's probably one thing I can do in here. Or I could have actually done something like vector 3D add or sum. Where's the math? Vector 3 add. Yeah, it's actually without the D. Center. I can do shit like that. So yeah, that's cool. So, and we also have the radius. And the radius actually must be multiplied by this, shouldn't it? Which is rather weird. Don't we multiply it in 2D? We multiply it afterwards. It's kind of weird. I could have actually done it like this. Like I don't really know why I don't do it like that. And plus I could do the same center plus in here too. Vector to add center. So I can do that as well in here. So, and bring everything to sort of the same thing. Okay, so we have a cluster generator, right? So let's define some sort of like a static samples 3D set, right? And we can try to generate some shit in there, right? So generate cluster, right? And its center is going to be, I think at 0. The radius is going to be around, let's say cube size, right? So this is a cube size, and let's generate like 10 of those things and put them into this set in here. So we just generated a bunch of 3D things around, so it's sort of like a cloud of, you know, things. So afterwards, what we need to do, we need to draw them, right? We need to draw them. So let's go iterate through the samples, size ti, 0, set count plus I. And we're going to have vector 3 it set items I. So we've got the thing, we're trying to draw it. And so we probably want to have like a sample size in here. Let's rename cube size to sample size, right? So because that's what we're going to be doing. Let's rename query replace cube size. Right, so sample size, and also cube color, so this is going to be sample color as well. And maybe what we want to do instead of cubes actually is to draw sphere. You can draw spheres. Would you look at that? All right. So that's going to be it. Sample size, sample color. There we go. That's what we got. And I want to make samples a little bit smaller. I think 10 is too much. Generate cluster. Honestly, I would like to generate like 10 of the sample size, like a huge thing. So vector 0, whatever. All right, so we got this thing. So that's what we got. A bunch of things in here. So there's a 10 points. So this is the 10 points that we generated. So maybe this is still too much. What if I say, well, I mean, we have normalized device coordinates which are from -1 to 1. So I think the sample size could be even just like 1. If you know what I'm talking about. So it doesn't really matter actually that much. So when I start the camera, the initial magnitude, let's also make it like 20 or something, so it's really far away right away. What about like 100? So I want it to be like, I want to be able to see the whole thing. Around maybe 50. Around maybe 50. And we can clearly see that. So that's pretty cool. And let's generate maybe how many of them? What about 50 of them? Let's generate 50 of them. All right. So this is sort of like one cluster that we have in here. Sort of like a one cluster. I'm still kind of not sure, like, I want them to be smaller, sample size. Yeah, so everything here really depends on the sample size. Everything here really depends on the sample size. What if we just don't depend on the sample size in here? Right, and also in here, just that. Because sample size is 1 anyway. So what if we make it half of that? Yeah, that's already better. I like it much better actually. So that's so cool. Okay, so generate cluster. So radius is going to be around 20, but let's generate 200 of those things. And it starts to get slower actually. So it's kind of difficult for my computer to, yeah, it's too many. I wonder if this is because there's too many triangles when I try to draw like spheres and everything. That could be the case actually, believe it or not. What if instead of sphere, I'm going to be drawing the cube, right? Because it's less triangles. because fear is just like very smooth. It is too smooth and it requires too many polygons. So let's actually try this thing. Yeah, it's much faster. I was actually right. Let's use cubes instead, right? At least for my PC. So when I'm scrolling around, right? So this is around. Let's make 20. Okay, that's cool. Now maybe we want to try to generate like an initial state. Like we want to generate more points. We want to have something similar to mouse dataset, if you know what I'm talking about. Right. Mouse dataset. If I do 2D, all right. Essentially, you have sort of like a central, like basically several blobs, right? But here we can have a central big blob and then two smaller blobs in here, so to speak. Right? We want to have like two smaller blobs in here. So let's actually try to do that. So in here, I can do vector 3, right? So this is going to be that. And obviously it's going to be 0, 0, 0. Another one. So if we're looking at X and Y, right? If we're looking at X and Y, so this is the initial sort of like a radius. So that means we can go minus that radius, right? We can have something like a cluster radius, which is going to be 20. Cluster radius, right? Minus cluster radius. So this is in terms of X. We go in terms of X back, and we need to go up a little bit. So that means it's going to be sort of like a cluster radius again. And here, cluster radius is going to be maybe half of it. And also, here we can have cluster count, right? And the second one is going to be half of that cluster count. And it's going to be 200, and this one is size T. So now, if I try to do that, can I see what is going on? This is a wrong thing, so 3D. Yeah, so we have one ear in here, right? So one main blob and one ear. So that works out really great. I really like that. So then we can try to generate the second ear of the mouse, right? So in that case, it's just that. And we should have the 3D mouse, right? So basically we have a set with 3 clusters, right? So here you can clearly see that this is 3 clusters. So that's pretty cool. Okay, so what we want to do next, we want to probably replicate the situation as in 2D, since we're going to be splitting it into several K clusters, right? Into K clusters. We need to have the K, right? So initially it's going to be 3. And we also have K sets of samples into like K buckets into which we put everything, and K means in here. And we also have different colors to assign to different clusters. So we have this sort of set. But this entire set is actually defined you know, in 2D terms. Colors, by the way, could be reused across both of the examples. I can actually move colors into commons. I think that's actually a pretty cool idea, right? So because it's like useful in both of them. So, but this sort of like a state, right? So in 2D example, it's 2D state, and here it's going to be 3D state, right? So here, as you can see, there's like this. They can be 3D. And in 2D, there is a function that generates a new state, right? So here we have that. I might as well actually do this kind of thing there as well. So generate a new state. So what is it going to do is just this. And what's funny is that we can parameterize cluster radius and cluster count, right? We can literally make them parameters of this entire function, like so. And when we are generating new state, we put 20, 200 in here. So that way we can do this kind of stuff. But furthermore, we also need to generate the means, right? And the means are those things that define the center of the cluster, right? So as you can see here into the example, they are the center of the cluster, and they are moving towards the centers. They eventually converge there, right? So we need something like that, but for 3D, right? And in here, we're going to be generating a random 3D point, right? We're generating a random 3D point, and it's like, what's going to be the sort of range? I suppose it's minus cluster radius plus cluster radius. Cluster radius, yeah, something like this. Cluster radius. So might as well just do something like this. There we go. So we generated a new state, and after we generated all of that, we also need to render the means. Let's go ahead and just go through all of the means, I suppose. Right, so let's go through all of the means. And here we have means I, and we're gonna draw a cube, right? We're gonna draw a cube, but the side of the cube is gonna be twice as much. I suppose maybe we can have a mean size and mean color. That makes sense. So this is going to be mean size, which is basically sample size, but twice of the sample size. Twice of the sample size. And this one is going to be white. Okay, good. So this is a wrong one. 3D. Go. So let's go through the compilation errors. Okay, so that's cool. So we have 3 random means in here, right? You have 3 random means, essentially. Okay, so there were some warnings in there. I want to go through them. Oh, this is because we don't use some of these things, but that's fine. In a 2D example, we had an operation of reclustering everything. We had an operation of reclustering everything. So, and reclustering is basically going and computing the length and stuff like that and fitting a particular point into a particular cluster. We want to have this kind of function in 3D, right? But that will require changing the vector on which we're operating. So we need to change 2 to 3, right? So, and that's the entire change, right? So, something like templates would have been actually useful in here, I think. Right, but it is what it is. So FLT max, I think it is located in floats, right? So it's a maximum value of a float, right? Okay, cool. So after we generated a new state, we need to recluster the entire state. So that's what we need to do. We're reclustering this entire state, and so all of the points are now located within the clusters, not only the set but also the clusters. So what we essentially need to render in here, we need to render each individual cluster, right? So we can do for size j, 0j less than clusters I items j plus plus j, right? And in here we're gonna have the point, right? So actually not j, what the fuck am I talking about? This is effectively the it, right? This is effectively the it, but this has to be the count, right? So we have it, and that's what we want to render in here. That's what we want to render in here, but we want to render it with the color of the current cluster, right? So when we have a limited amount of color, so we want to actually wrap around this kind of stuff. So essentially now that will make all of the cubes colored according to the cluster they belong to, hopefully. We'll see how it goes actually. Yeah, there we go. So as you can see, they are colored depending on the cluster they're currently in. That's kind of the point. That's kind of the point. Okay, so, and now there is a last operation in here, update means, right? So, and this is something that we have to do iteratively to sort of like find all of the necessary clusters, right? So it's pretty easy. Just replace 2 to 3, right, like that. But there is one problem in here. If we end up with a cluster that is empty, we won't have enough information to actually update the means. So we need to regenerate the means, and we can only regenerate the means if we know the cluster radius, cluster size, and stuff like that. Like, yeah, cluster radius and cluster count. So we have to pass those things to the update means. And the way we regenerate this entire stuff is like this. Just like this. Just like this. Update means. And how do we update means? Update means. Yeah. So we update the means and we recluster everything on each frame. So that's basically what's going on. So we might as well factor out these things to cluster radius, I think it's a cluster radius. Cluster radius 20, so it's going to float. And to be fair, we don't even need cluster count for update means, but that doesn't really matter. So cluster count, update means, cluster radius. And I also said that I want to provide cluster count, but I feel like the count is not needed here. Yeah, it is not needed for update means. It is actually not needed. So let's actually not do that. All right, so let's maybe zoom in a little bit. All right, and now when I press space, something went completely horrible. I don't know what the fuck is going on, but that didn't work. That is rather surprising. Okay, wait a second. So what is going on? Oh yeah, I see. Yeah. Because we're also supposed to divide by count z, and I forgot to do that, right? So that's basically what's going on here. So that should solve the problem, I think. Yeah, there we go. So we identified all of the clusters correctly, as you can see. We identified all of the clusters correctly. So this is a k-means clustering algorithm. We already implemented it in 2D, right? So that was pretty straightforward. So this is 2D version of this thing. Right, so this is 2D. But now we also implemented it in 3D. And why I wanted to have it in 3D? Right, because I would like to do color quantization, right? So essentially you load up an image, you load up colors of the image in 3D color space, and then you identify the clusters and you use the clusters as the palette, those reducing the size of the image, right? So, and I could do that without any visualization. It's actually super easy to do without any visualization, but it's not that interesting, right? It's really not that interesting. It's kind of way cooler, would be way cooler to see, right, the actual clusters in here. But now we have a way to visualize this entire stuff, right? We really have a way to visualize this entire stuff, and I think it's super cool. Right, so, okay, I'm already streaming for 2 hours. Let's make a small break. And after the break, what we're gonna do, we're gonna load up a PNG image, collect all of the unique colors of the PNG image and put it in this 3D space, visualize, and try to do k-means clustering on that 3D space. There will be a lot of points, right? So we just generated a random garbage, right? That has nothing to do with the reality. Let's try to do that on real data. Sounds good? Sounds Gucci? Sounds what? Tamaguchi? All right, so let's go ahead and load some images. How about that? So what we can use? We can try to use the Lena image, right? So, but in 2023, you're supposed to use the ethically sourced Lena image. So let's actually get that one. So yeah, we're gonna get it from here. Gets me every time. So I'm gonna put it in the description for anyone who's interested, right? So this is the ethically sourced Lena. Right, so let's go. It's a WebP. I want a PNG. So let's actually go with 512 by 512. Right, and yeah, so this is what we're gonna have in here. And I'm gonna just wget this Lena. Does she have OnlyFans? I don't know. You can ask her. Beautiful. So now, I suppose the reason why people use Lena all the time, I heard that the image itself has like a very specific properties. So I wonder if that recreation also tries to recreate those properties, like very valuable properties of Lena image. I don't know what those properties are, right? But yeah, people say that it's actually very useful for testing things. It's actually very useful for testing. Anyways, so as far as I know, in Raylib, you can just load the image, and you can just get the image. So which is pretty cool. We'll need to actually distinguish between like two modes, right? Because we have a mode that just generates random points to test things out, and the one that loads Lena and tries to sort of come up with a palette for Lena. Right, so maybe I'm gonna introduce something like Lena, right. And in here, if you are in a Lena mode, if def Lena, lin lin and min, right. Lena. Anyway, so and if then load the image, and so this is yeah, it's Win32. I forgot that it also has a prefix. Yeah. So Win32 Lena and Mena. Lena and Mena. There we go. So this is the image. We just loaded up the image. So after that, if we take a look at the definition of this thing, you may notice, very interesting, is that the pixels are void. The pixels are void, so we don't really know their format. I suppose it depends on the format. So in a pixel format, so let's take a look at the pixel format. To be fair, I would expect specifically this format. So uncompressed, right? Is it uncompressed? So RGB, yeah. I would like to prefer to work with this specific format. And one of the things we can do after we loaded the image up, we can say, well, format has to be equal to that, and we can literally assert that. All right, we can literally assert that. Okay, now I'm going to try to run this entire thing. Is it going to load successfully? Okay, so it did in fact fail. So this is because it's R8, G8. Yeah, this one is weird. Wait, that's such a weird format. Oh, it's more of a float thing. Yeah, so this is not what we want. This one. To be fair, I would like to have like a 32. But they kind of force this format upon us. All right. They kind of force this format upon us. And so R8, G8. So what that means, if I want to be able to, you know, convert it to something, is there like a load image? Format. Image format, new format. So convert image data to desired format. So this is one of the things we can do. Another thing we can do, we can turn an image into pot. Very useful. I don't know what it is. It's a power of 2. Oh, I see. So convert the image size to the power of 2. You know why it's needed? You know why it's needed? So it is needed for MIP maps. Right. So because they has to be power of 2. It's actually kind of funny. So what I want to do, essentially, since I can just convert to any format that I want, I can just simply do something like this, right? And I don't even have to check anything in here. I don't have to even check Scheiße, meine Freunde. So let me see. So I'm going to take a look at the logs. Right, so image. So where's the Lena? Yeah, there we go. So yeah, loaded successfully, and one MIP maps and stuff like that. So we are Gucci, we are in fact Tamaguchi. So that's pretty cool. So the next thing we need to do, we need to collect unique pixel color, unique colors essentially, right? So we need to collect unique colors. So to do that, we'll need to have some sort of a hash map, right? So I wonder if Raylib has some sort of a hash map, right? That would be cool. But I think it doesn't have any hash maps. Right, okay, let's actually use stbds, stbds.h. Right, we're going to be using this hash map. I don't know why Chromium is so slow for me today, but yeah. So even my 3D application is faster than Chromium, so I mean, it doesn't really do anything useful. Come on, you can do that, Chromium. I believe in you. I believe in you, Chromium Summer. Okay, wget, and let's download this scheiße. So how we're going to be using all of that? We need to include stb ds. And all of these noobs from Reddit keep crying, oh, C is such a hard language, it doesn't have a hash maps and stuff like that. There you go, it has a hash maps now. 5 seconds. Hash maps. Hash maps. Hash maps. Easy peasy. Lemon squeezy. Stop crying. Start coding. Freaking start coding. I'm sorry. Been streaming for 2 hours, right? So I'm already going a little bit crazy. So how this goddamn hash map works, right? So you need to have like a cell in which you're going to be storing the keys and the values. Let's actually take a look at this thing. So there is a non-functional API somewhere, right? So, and basically you have to define the type T, and the T for hash map specifically must be a structure. It must be a structure. Declare the empty hash map of type T, access functional interface. Alright, cool. Oh, here it is, I see it. Okay, so given T is a structure type, so it should have tk key and T value. Note that some functions do not require TV value and can have other fields. Right, so essentially we can say something like caller point, and it's going to be like literally this. Okay, and now we can have caller point, and we can say that this is unique caller points. Maybe unique points, right? Because I don't want it to be too long. And there you go. This is a hash map. This is a hash. We just defined a hash map, right? So then we can start iterating different points, right? So we can maybe define something like this. We can even use the caller from Raylib instead of uint32, right? So the definition of the caller from Raylib is this, which fits perfectly into uint32. So we can even do something like that, right? So this is a caller point. Then we can also have something like caller points, right? And then we can take image. And I don't remember how they're called. They're called data, and we can literally just convert that. So afterwards, I probably want to do it in here. We can start iterating all of the points. Like, it would be nice to have maybe points count, and points count is basically going to be image width multiplied by image height and stuff like that. I said height. So there we go. So we can just start iterating like this, and through each individual points, right? We want to check if that point is present within the unique points, right? So what kind of functions should we use for that? I think it's something like hash map get I or whatnot, or maybe hash map get. So this one accepts the key, it accepts the key and returns the value corresponding to key in hash map. So, and I suppose if it's missing, it's going to return maybe 0, but maybe we have to use get I, right? Because it returns negative value in case the key is not present. So that's the function that we probably have to use. Right, and essentially what we do unique points, right, point I, and that gives you the point diff index. And here's the thing, if that index is less than 0, the point is not in hash function. That's how easy it is. Yeah, that's it, literally. I'm not even fucking joking. Like, I'm not joking. That's how you use this hash map. So in C, single file, header only file. Come on. Isn't that cool? Isn't that poggers? I know it doesn't fit the propaganda on Reddit, but I mean, still pretty cool. So let me see. How do we add shits? I'm pretty sure I'm going to stumble upon some sort of problem, right? With this entire thing, but we'll see. Okay, so what we want to do in here, we want to just put something, right? We can put an entire item in here, right? So like so. So we put unique points, but we first have to create the color point, right? So item, and this one is going to be simply points I, the same thing that we used in here, and we can just push this entire thing. And that effectively means that we just collected all of these things, right? We just collected all of these things. And then we can answer a very interesting question. How many of them do we have in there in this thing? So I think it's hm_len. Yeah, hm_len. So we can say something like this. As let's actually factor out this thing to lenapath, const char lenapath. I'm gonna put it like that. 4. Okay, so we can say this thing contains ZU unique colors, and we can do yeah, we can do lenapath, and we can do hm_len unique points. And after that, we can actually exit, right? So basically, I'm gonna sort of comment out everything after that temporarily, because the only thing I care is how many unique colors you have in here. Okay, let's see if it's gonna crash or not. So maybe it's gonna be terrible. Who knows? So it's a single image actually. Yeah. So this thing contains this much unique colors, which is rather interesting, isn't it? Because if we take a look at the... That's a lot of unique colors if you think about it. Right, so what is that? Huh. Yeah. So it works. So I'd like to maybe take something that contains less unique colors, just to test how, like, if the hash map works properly, right? I'm just curious if it does. So something like Tsojing Pog, right? I think it contains less unique points. So let's actually go ahead and try to do that. So I'm gonna do wget, and is that how we do that? Tsojing Pog PNG. Do you have PNG? There we go. Here is the Tsojing Pog. Is it really PNG? Let me double check. It is in fact PNG. Maybe it would make sense to actually create a folder with images. Right, I'm gonna move Lena and Tsojing Pog in there, and we could just accept the path to the file as the command line arguments. I think it would make a lot of sense. Right, so let's rename this thing to file path. Let's go through compilation errors because I think it's gonna be easier to rename it like that, file path, and the last one is going to be file path. There we go. Right, so yeah, let's actually accept file path as a command line argument. So it's going to be int argc argv, and the first thing you have in arguments is actually program. Right, let's actually just take it out. Knob, I think it's shift arguments, knob h, knob shift args, argc argv, right? And then what we can do, if argc is less or equal than 0, we have to do something like knob log knob error, no input image is provided. We don't have to do that, and we just exit with 1. Otherwise we can do knob shift like that. And that should work. So no input image is provided, so we can do image Lena now, right? And it says Lena has this amount of unique colors, and then we can say Tsojing Pog, and it should have like few 1267 Unicores. That's kind of sus, isn't it? That's kind of sus. Though, if you compare it to the actual size of this thing, so where do we get so many Unicores? Is that from the anti-aliasing? It could be from the anti-aliasing and the shades of gray and stuff like that. So that, yeah, okay, I can see where all of these unicolors might be coming from. But if we compare the actual size to like the full thing, yeah, okay, so it's like a 1/10 of this thing. 1/10 of this thing. We can try to create some sort of like a very simple image. I wonder, but to do that with something like Krita, it's actually a huge pain in the ass, right? Because Krita is so goddamn overbloated, it will take half of an hour to just load it up. The logo is cute though. Acipride, do I have Acipride? I think I don't have Acipride. Yeah, I don't have Acipride here, unfortunately. Goddamn, my paint is weird with like specific sizes of the images and shit. Just like I don't like to use that. My paint is good for just like drawing on the screen, but producing images is kind of But to be fair, this is unacceptable, honestly. Like, what the fuck, right? So kill all Krita. Yeah, fuck you. So yeah, that's a problem. That's what I'm talking about. It's just like it doesn't have boundaries, and it's weird, and it's just like, yeah, I just want to have maybe 2x2 with the same color. How can I produce such image in 2023? I don't freaking know. Right, so maybe we can use ppm, right, and just like manually do that. I don't fucking know, honestly. So ppm, so there were some formats, right, different formats. Нет BPM. So there is a ASCII format. Okay, so P3. So ppm P3. Not PM, ppm. God freaking damn it, bro. Okay, so maybe that's one. Just give me an example, bruv. Okay, so we got that scheiße. So I can just do that. Right, PPL, right, and it's gonna be PPM. So let's say 4x4. I'm gonna query replace this shit with 15, 15, 15. Not 15, 15, but rather maybe even 0, 0. Right, so this is gonna be red. And this one also gonna be red. Oh. PPL. Yikes. Unable to read PPL, PPM, no images defined. Though Emacs is capable of reading it though. Look at that. Emacs is capable of reading it. But ImageMagick is incapable of converting it. I was just like, bruv. Like, why doing something like that is so goddamn fucking hard in 2023? I have no idea. So, do we have something like a save image? I might as well just download STB image and generate this motherfucker myself. That's just easy. That's just fucking easy. That's how bad everything goddamn is. That's how bad everything is. It's easier to just, like, you know, write a C program and it's just STB this motherfucker. And what's funny is that I don't need anything extraordinary. I need once once in my life generate 4 pixels and forget about it. Fucking forget about it. And I can't even do that easily. You need to open some overbloated website. You need to download some overbloated shit. You can't just generate fucking pixels. It's annoying. It's frustrating. That's why everyone hates computers. Everyone hates programming. Okay, so STB image, right? Pixels, C. Right. So because essentially what I want, right? 32T pixels. Look at that. Right. I have like a red color, and I just wanna have 4 of them. Just 4 of them. Just 4 pixels. It's just simple as that. Why is that hard? Why is it so fucking hard? I don't fucking know. stb image.h. Find stb image implementation. stb image. stb. Oh, it's actually right. Get them. We need a different library. Yeah. CBI is right. And what I can do in here is just pixels. PNG size is 2 by 2. Amount of components is 4. The data is the pixels. The stride is 2 multiplied by 4. And that is literally it. That is literally it. CCO pixels, pixels C, pixels. Is it gonna do thing? Is it gonna do thing? We have to link with mathematical library. The mathematical library is needed. Undefined STB image. Yeah, this is because it's right. Image right. Thank you very much. And I can forget about that forever. That's what I want. That's literally what I want. It's fucking literally what I want. Why is it so fucking hard? Like, why do I have to have overbloated shit to just do that? I don't fucking understand. Anyways. So there should be one unique color. Should be one unique color. And so pixels, PNG. How many unique colors? One unique color. So finally, we managed to test our hash map, and it works beautifully. It works beautifully. I'm super fucking happy. Holy shit. Anyways, so now once we gathered all of the unique colors, right? Once we gathered all of the unique colors, we want to put them into the set, right? So we have a global set thingy, right? Static, maybe samples 2D, samples 3D set. That's what we have. That's what we have. We want to put all of these things there. So how can we do that? We can actually, as far as I know, this thing allows you to access those unique points directly. So the thing you can do is just something like this. Maybe we could have unique points count, which is simply unique points count this. And let's actually just print them, right? So because I want to see them, so we're going to print them as hex, padded with like 8 zeros. So the width is going to be 8 characters, right? So and they're going to be padded with 0. So these are the colors, unique points, I key, right? And let's actually see all of the unique points in here. So in case of the pixel, what's up with that? So I suppose we need to reinterpret this entire thing. Okay, so I'm going to reinterpret it as uint32 pointer and just do it like that. That's fine. So you don't have int. Let's include that. let's include that. What else do you want from me? You want from me the caller HM unique points count. That's what you want from me. There we go. So here is the only unique caller in here. That is totally fine. That's expected. But now, what about sodium pog? Sodium pog. Here are all the unique callers in here. Here are all the unique callers. Okay, so we want to convert them to actually vectors. We want to convert them to vectors. How are we going to be doing all that? That's a very interesting thing. Do you care about alpha channel? Personally, I don't want to. Right. So for now, I'm going to ignore it, right? Because that means I have to visualize in 4D space, and I don't have a capability to visualize in 4D space. So we're going to basically cut out the alpha. That's what we're going to be doing. All right. So I'm just iterating through all of these things, and I'm going to take the unique caller. So this is going to be R. And I might as well just make them from 0 to 255. Who said I can't do that? I can do that. Why not? So sounds pretty good. So vector 3 sample, right? And this sample is going to be X, Y, G, Z, B, and we've got that. So then we can do nob da append set sample. There we go. So we generated all of that stuff. So we can start with just pixels because it has one unique color, right? So yeah, it doesn't like, oh, is it red, green, and blue? Gray plus alpha. Thank you, Emacs, for auto completion. Very cool. What else do you want? What is it called, bruv? Color RGBA. Okay, so you didn't like that they're not floats. Is that what you want? Ah, because it's a key. That's what you want. Okay. What else do you want? What else do you want? Semicolon. Yeah, bro. Okay. Come on. You can do that. What else? What else do you fucking want from me? I accidentally put N in here. Just compiled it already. Yes, thank you so much. Okay, so we get that shit, but it's kind of weird, right? So when we generate a new state, we should not generate if not defined Lena. So though, to be fair, it's not called Lena anymore, right? So let's call it image. Oh, where's Lena? Image. Where's another Lena? Image. Image. So that's it. So that's what we're gonna be doing in here. Okay, so we can't see Scheisse because I think that point specifically is way too far away for us to see anywhere. So let's go ahead and just apply the sodium pog. That should give us more points, hopefully. Yo, what the fuck? Yeah, it's from 200. Okay, so that's basically all of the points of that image. So we can, okay, so we're starting to quantize it into 3 things. Yeah, that's kind of funny. So, and that's how we can cluster it in 3. Yeah, it's kind of interesting. Yeah, because there's not that many colors in there. There's not that many colors. Okay, so what about Lena now? So let's take a look at the Lena. How many colors we have there? Oh shit, it's, oh my fucking goodness, what the fuck, bruv. It's too much, it's fucking too much. My computer is fucking dying. But yeah. 100k, yeah. It is too much, actually. I wonder if we can scale it down. Scale it down a little bit. Right, what if I convert Lena resize 32? Right, so it's going to be Lena 32. Let's take a very small Lena. PPL Lena. Look at that Lena. I mean, yeah. So how about this Lena? Is that a good Lena? Yeah. Look at that Lena. Right, so, and let me see. So I'm gonna just do 32, and that should be a little bit better, right? So these are the points. Okay, so that's actually pretty cool. Maybe it would make sense to, when we're rendering those things, to just map them slightly differently. Right. Okay. So it's like a huge thing that goes there, as you can see, right? Yeah, that's a very huge thing. But now we're clustering it, and we found like 3 clusters in there. I'm not sure if they're visible really that well, but I like to be able to like fly around them. So we need some sort of like a free camera or whatnot. So we already found 3 clusters, as you can see. So can you see them? So this is like the red cluster, this cluster, and this cluster, or something like that. So it's pretty cool. So now, what if I actually convert these things into something more, like from 0 to 1, right? When I'm generating the clusters. So I can just simply define them to 255 0f, and that's basically that. All right, so that will make them, yeah, that made it rather small, right? So that made them rather small. And another thing I can do now, I can multiply it by maybe, what about cluster radius? That's a good idea. I can move this thing in here and do the cluster radius. So this is a very good constant that could be useful for this kind of stuff. Yeah, that's much better. And we found 3 clusters in this image, right? So, well, I mean, we said find 3 clusters here. And it found it. We can reduce the size of the sample size. Let's make it, you know, 1/4 of 1. That's much better. So that's basically the thing we have in here. So that's pretty cool. Here are the classes. Okay, so let's imagine let's imagine that we want to have a palette of 16, right? Palette of 16. So we want to split this entire stuff to 16 colors. Can we do that? Well, it's struggling to find 16 colors, but this is probably because we don't really have that many points. So the image is too small. I think we need to have different sizes of Lena. Right, so we can do 64. Let's actually try 64. Right, Lena 64, a little bit bigger Lena. Okay, so this is a little bit bigger Lena. Let's do 64. Okay, so this is a little bit more points, hopefully, right? Because more resolution and stuff like that. But eventually, hopefully, it finds some of the clusters, right? So as you can see, some of the centroids are just moving around because they can't really fit, right? They can't really find the cluster for themselves. So my goal is to have the situation when all of the centroids kind of found their place. Yeah, so around here. So this kind of separation of things is pretty good. And you know what would be even cooler? If instead of like random colors, we use the colors of the points themselves. We do kind of have information about the color within the point, within the centroid. We can actually recover it. So we use cluster radius to do this kind of thing, right? So it's, yeah. What we can do, we can take the mean, and try to recover color from it, right? So x is from 0 to cluster radius, so we can divide it by the cluster radius, convert it from 0 to 1, and multiply it by 255, and just assign it to red, right? And green is going to be y, and blue is going to be z, right? And essentially, we can do color, like this. And alpha is, of course, 255, right? So something like this. And instead of these colors, we can just use that. right? So we're literally using the color of the image, so we can clearly see the colors of Lena, hopefully. We'll see how it goes. So this, yeah, there we go. So these are the colors of Lena. Do they look like colors of Lena? I think they do. These are the colors of Lena, look at that. Right. That's pretty cool. So I would like to even increase more resolution, right? So what about 128? 128, so even bigger. Yeah, so let's actually start working with this size of Lena. Right, 128, and we have to go here. All right, it starts to lag a little bit, but not too much. So I suppose when you just have more of these things, I feel like when we're generating the means, yo, that is so fucking cool, bro. Okay, so we found this sort of distribution of these things. We found the distribution. Yeah, okay. So, and we can turn this into palette. We can now turn this into palette. Right. So essentially, go through each individual pixel. Go through each individual pixel and check which cluster it belongs to. Which cluster it belongs to. And use the color of that cluster. And the color of that cluster is the mean. Right. And then you can maybe save it to the format that supports palettes, right? And this specific sort of array of colors should be really good representation of the image itself, right? It should be a really good representation itself. So we can try to do that. Actually, we can try to do that. This is kind of cool. I really like that. I really like that. So yeah. I wonder if it's going to be too slow. We need to assign some sort of a point, some sort of a key. We need to assign some sort of a key. So let's actually do if is key pressed, maybe key S. And this is where we can try to do that. This is where we can try to do that. We can modify the image directly, and that is probably fine because we have a copy of that image in a set anyway. So that's fine. So I can modify this thing directly. So, all right, let's start iterating through the points one more time. So we had this kind of thing, right? So we have points and points. We already have this thing, right? So that means I can just start iterating in here. Size t 0 points count plus I, and there we go. So the only problem here is that how can we check, how can we know the cluster of color? Right, so I can provide the color in here, and I want to know the cluster of this thing. So what cluster does it belong to? It might be even something like negative or something. Right, so in that case, if k is less than 0, we can maybe knob log knob error. Could not color out of cluster, right? We're not gonna crash, but we're gonna break out of this loop, right? So we're just breaking out of that loop. To be fair, I'd like to break out of everything that is happening here as well. But that is only possible if we, yeah, I don't know how to do that, but we'll see, But maybe that's fine. Let's just like maybe log that and don't do anything. Okay, so you found the cluster. So then you can just take the color of that cluster, and the color of that cluster is just literally this, right? So it's literally this. We can just use K in here, and there you go. Here is the color of your cluster. Here is the color of your cluster, and then you can take the points I and assign the color of that cluster. That's how you bring everything to the same thing. So after that, we need to save the image. But as far as I know, Raylib doesn't expose anything for saving image. Save image. Right, so there's a load image, but you can't really save image. A dump image. Is that unload image? Unload image just deallocates the memory. So there is a way to do screenshot. So take screenshot. Right. And it can save things, but it doesn't allow you to save your own images. Maybe it uses something that we could reuse. I just don't know the name of this thing. So Raylib src. Let's go here and let's do grep rn. I want to see implementation of these things specifically. What do you use? RL read text format. Export, of course! Of course it's an export image, you dummy dum-dum! Of course the opposite of load image is export image, not save the image. You dummy dum-dum! Obviously! Obviously! Oh my god, silly me! Silly me. Imagine thinking that opposite of load is save. Imagine thinking that. How deranged have you have to be? I don't know. I don't fucking know, mate. Anyways, so I'm sorry. So yeah, we export in the image and stuff like that. All right. Let's give it a try. Let's give it a try. So I wonder if it's going to be too slow. Okay. Okay. Cluster of yeah, I still this thing not implemented. God damn it. Yeah. So you're given a color. You're given a color, and what you want to do? Honestly, I think you can basically treat that thing as clustering, right? So we already have an operation in recluster, and we just iterate through all of the. Within each individual point, we're iterating each individual cluster, and we see to which mean it is the closest. And that is basically the algorithm that we want to have in here. Right. So, okay, cluster of color. So I'm going to literally copy paste it, right? So because I think, and what's funny is that it's literally has a key K that is minus, okay, this is perfect, right? So this is literally perfect. Okay, so you have the color, but then you need to convert color to P. And how we convert color to P, right? So we have to deal with this entire thing. Right, where's the conversion? Yeah, that's how we do it. So this is the color. So there's a couple of things that I would probably like to factor out into separate functions because it does make sense. It does make sense. But not for now. I think I can do that later. It's quite surprising, right? So we could implement reclustering in terms of this function, by the way. We could implement reclustering in terms of this function. I don't see any problems with that. Right, okay, so cluster, this is just a warning, nobody cares. Subtract P, well, it has to, this is the P, sample is P. That's pretty cool. Cluster, why are you still showing me that? Okay, so this is the cluster count. Is it cluster count? Yeah, cluster radius. This in fact cluster radius. What else? All right. So what are the warnings? What are the warnings? You have program that is unused. Can I? By the way, does it work in C if I put underscore in here? Wait, it doesn't. That would have been actually kind of cool. I think that would have been kind of cool, but it is what it is, and it isn't what it isn't. I wonder if I can do some stupid shit like void cluster count, right? So, because that's easier. Just a second. I want to get rid of the warnings. I'm sorry. They bother the heck out of me. All right, they bother the heck out of me. So, and yeah, maybe I can just do something like this. Not all of the warnings. Well, I mean, generate classes is not used in this specific case, but maybe I can do something like void generate cluster. Like this. Those they want colors are unused. Whatever. Okay. So I'm fine with that one. All right, let's try to quantize everything. Let's try to quantize everything to the point when we don't have any weird things that are jumping around. At some point, we're gonna find... Okay, so there we go. So all of these centroids are perfectly fit. So we can continue iterating, right? And it will find a better and better approximation for the colors, right? But at some point, we can just stop. Right, so I'm pressing space and it keeps approximating, and I think here it doesn't really change anymore. So now I can press S and, okay, so I think it already generated the thing. So, and now we can take a look at that specific image. Right. So, what the fuck is going on, honestly? Just a second. Put PNG. Why on earth would you make it like that? Is so weird, but anyway. So this is Lena with 64 colors, with 16 colors, I'm sorry. It even has a little bit of a dithering. Holy shit. What the fuck? This is so fucking cool. And now if I open the other Lena, so images, 500, actually 128. So what I want to do now, I want to put them side by side. Right, so this is the original. Well, it already had some sort of a dithering. Okay, so, and this is with 16 colors. So this is super cool because this is full colors versus 16, and 16 looks decent. It still looks decent. So that's what's cool about it. That is insane. Holy shit. We can have less colors, by the way, chat. That's what's cool about this entire shit. We can keep reducing the amount of colors. What about 8 colors? What about 8 colors? Let's see. All right. Only 8 colors. Let's just let it do the trick. Last cluster cannot find. Okay, so last cluster found its place. All right, so this is only 8 colors. It still learns a little bit. I think it still learns some stuff. Okay. All right, let's save it. And take a look at this entire thing. All right. This is 8 colors. Still looks good. Still looks decent. More or less. You can see that the quality is less, but I mean, it's still representative of the image. All right. Let's keep decreasing the amount of colors. What about 4? 4 colors. Let's see. Okay. There we go. Let's try to find. So only 4 colors. It's actually quickly identified like the major color. Yeah, it is sort of like the key colors. This sort of like a red, dark red, this purple, and the 2 shades of beige or something, right? So it quickly identifying them, right? And it converged basically. So let's actually save that and open this entire thing. And yeah, so this is the original image with just 4 colors, and it picked four colors perfectly. It's actually kind of insane how perfectly it picked them, right? This is like the main major colors. This is so cool. I didn't even expect it to be so fucking cool. This 3D visualization makes it even better, I think. You can clearly see like these things. What about 2? Yeah. So let's actually see if we can do 2. I think 2 is gonna be like the last thing. Right, I didn't think it's gonna be... It is gonna look really good. Okay, so that's not a bad idea to use these 2 colors, right? Right, so let's see. Not bad! What's funny is that it's such a simple algorithm, but it finds like a very good approximation of the colors. Like, holy shit. What the fuck? It's not bad, right? For 2 colors, right? If you have to pick 2 colors, I think it's good. 1 color now, I mean, it's just... Like, I mean, it's gonna be an average of all colors. It's like, yeah, it's like a mean of all colors. I didn't think 1 makes that much sense. Now do HSV instead of RGB. I don't know. We're already doing that for 3 hours. I think RGB is more than enough. All right, so that's pretty cool. So let me quickly recompile that with maybe 8 colors. Right, so let's take a look at the 8 colors. So yeah, that's the result of today's stream, right? I think it's a pretty cool application of k-mean clustering. It is an insanely cool application because you can clearly see the usefulness of the algorithm, right? Right, I really like to implement this kind of thing. It's not just like some theoretical shit, right? So you can see that in practice, right? And with 3D visualization, it's actually super cool. I also like how easy it is to throw like a little bit of a 3D visualization in Raylib, right? So you can literally see how it all goes. So it's pretty cool. It's pretty cool. So the next stop, hopefully, is going to be the gzip paper, right? The gzip paper. So for those who doesn't know, right? For those who didn't watch the previous stream, there's another cool application of k-means clustering algorithm, not only for coming up with a palette for the images and stuff like that. So apparently you can quite easily classify different documents using k-means clustering, and simply by gzipping the documents. I didn't read the paper yet, but from what I read, so you can just take the gzipped version of the documents and do k-means clustering, and that will be a pretty good classification of the documents on different topics and stuff like that, apparently. Right, so I haven't read it yet, and this is going to be the next thing that we're going to try to do with this algorithm. I wonder if the 3D visualization is going to be helpful for us. Maybe it will, maybe it will not. I don't know. We'll see. But in any case, that's it for today. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you all on the next recreation programming session with Mr. Azuzin. I love you.